had one more example that I wanted to do, but my last video got too long. I couldn't tack it in there. So let's say that we have a wagon and we're pulling that wagon down the road. The angle that we've got a hold of the handle makes a 40-degree angle with the horizontal. And we're told that we're using a constant force here of 15 pounds to pull that wagon as we're walking along down the street. Now the question that it's going to ask is, what's the work that I do if I want to move it, how far? I want to move it 500 feet. Now the thing that I'm sure we've encountered it in another section, I can't put my finger on what number section it is, but we know that the work that gets done is the force times the distance. So I'm going to need to find my force in this x direction and multiply it times the distance that I'm pulling the wagon, which is 500 feet. So this one's a little bit boring because my component form, what I'm breaking it into is just component form of the vector. And because my orthogonal vectors are going to be horizontal and vertical. So I'm going to call my v, that horizontal vector. You could call it 1, 0 or 10, 0 or 0.7850, but we know we're moving left and right, straight to the right actually, and up and down 0. So if I want to find my W1, like we just wrapped up doing in the other video, we said we want to project this force component down onto the V. We know that if we want to project the F onto the V up above on the numerator, we need to have the dot product of force and that vector V. Well, I don't have the component form, my x's and my y's. I don't have it written in pointy bracket notation. So if I think back to my last section, we know if we take the magnitude times the cosine of the angle, that gives us our x component. Our magnitude times the sine of the angle gives us our y component. Which if we hit those buttons on our calculator, this is just shy of 11.5. And the y component is 9.64. If I take the dot product of the v and the f, I get 1 times 11.49 plus 0. So I get 11.49 for that dot product. The magnitude of v is also boring because it's 1. And so this is the direction that, and the length, this is how I'm going to stretch my v. All right, that's my W1. I really don't need my W2 in this example because all I'm worried about is the work done, which is the movement, the horizontal movement here. So if I want to find the amount of work done on my object, I know that the force that's exerted on this guy looks like this. Okay, the distance that I'm traveling is going 500 feet straight to the right. And if I find that dot product, 11.49 times 500 is 5745, plus 0 times 0 is 0. Okay, work units are always strange, but I have 5,745 foot-pounds of work that's done to move that wagon straight down the road 500 feet. in your book, if you read through example 6, example 6 is a really good example about something sliding, keeping something from sliding down the hill. Okay, where our components, one of them is at an angle and the other one then is orthogonal to that, and it gives a good example of that. So I feel like the bases are covered after watching those two. Okay, if you struggle with dot products, if you're struggling with the projections, understanding their application, again in a physics class, that's really what it's been almost 25 years. It's been more than 25 years since I've had my physics class, but um, we found component forms, we found projections. You had to find these x and y components or these trajectories here at an angle. So this is an important topic if you're going on in a math class. But again, in trig, we just kind of hit the tip of the iceberg and say, hey, look what we can do. So let me know if you have questions.